Hey gang, logistic regression, more stuff. So we saw in the previous video that we have we have issues, right? If we try to model the binary dependent variable with simple linear regression techniques that we studied before. So in other words, to combat the violation of the assumption of the normality, or I should say the normally distributed errors, we're forced to use an alternative error distribution. So let me say that one more time. To combat the violation of the assumption of the normality, I should say normally distributed errors, we're forced to use the logistic regression model. So first of all, there are 5 properties of this distribution that I want to talk about, and I found it easier. I think I'm just going to, I took a screenshot, so let me just bump into this and we'll go through and talk about it a little bit. Make it really, really large so you can see it. First thing, let me back up here. This is actually given more in general about the probit response function. We're focusing on the logistic regression. If I really did logistic regression, it gave it its due, then I probably should have gone over this, but you know, I needed to cut the videos down as much as possible. So these properties still hold. So the logistic mean response function is bounded between 0 and 1, and it approaches these limits asymptotically. As our estimate for beta 1 increases, the mean function becomes more S-shaped. I'll show you some examples of varying B1 and B0 here in just a second. In fact, it's not even really a bad idea to maybe do that right now, since we're talking about it. Notice the graph on the left looks at a logistic regression model when beta 0 is equal to 0. Makes kind of sense. You know, most of you are teachers, so high school teachers, sometimes even community college. And if you were teaching this, teaching linear regression, or just linear models, slope-intercept, what you would do to give students an indication of the impact of changing the intercept and changing the slope, you would give different models with different slopes and different intercepts and show how the graphs are different. So in the spirit of that, that's kind of what I'm doing here. So you can notice that when B00, we have an go through y equals 0, right? But you can notice when B1 varies, as the B1 gets larger, we have more of what I would call a slope. So we could say that the tangent line right there is going to have a higher slope than it would for B1 equal 1. Notice what happens over here when B1 is negative 1. Then we just flip and start. Kind of reminds me of trig functions in a sense. And notice the impact on beta 0 being 0 and beta 0 being equal to 5. So it gives you, I think there's going to be one homework assignment where you're going to be asked to examine a logistic regression model with different values for beta 0 and beta 1. And hopefully by the end of this video you'll be able to easily do that, probably on your graphing calculator. Alright, so changing the sign from positive to negative, I can't say that any more than what the picture, we might say, spoke a million words there. Increasing and decreasing the intercept shifts the mean response function horizontally. Again, kind of reminds me of a trig function. But I think the most important thing here, other than the first two, is the symmetry property. And this holds true for the logistic response function. So if the response variable is coded where, say, y sub I equals, well, y sub I prime equals 1, easy for you to say, right? 1 minus y sub I, that is changing zeros to ones and ones to zeros. We can see down here that the symmetry of the normal distribution follows and stays the same. So extremely important that coding your zeros as non-success and 1 as success, or interchanging those doesn't change things. All right, let's get back to the good stuff. Well, it's all good stuff, but let's get back to actually the intent of the video. All right, so let's examine the density of the logistic random variable. So let's write this out. So let's examine the density of the logistic random variable. E sub L when the mean equals 0 and standard deviation, we'll just choose something wacky, is say pi over the square root of 3. All right, why pi over the square root of 3? Just because. All right, the simple form, and we could have used anything there, is the density function with respect to E sub L will be E sub L over 1 plus E raised to the E sub L. Two different E's there, obviously. And the cumulative density function we'll give it capital F sub L of E sub L is just E sub L over 1 plus E sub L. Now, where do I want to go with this? Okay, I got it. Our E sub I let's use C. Yeah. Has mean 0. And standard deviation, just to be consistent. So the probability that y sub I is equal to 1 would be the probability that E sub I C over sigma C is less than or equal to beta 0 sub K. Now beta 0 sub star plus beta 1 x sub I star, where, guys, it is so hard to see the way this is configured. I wish I could take a picture to see where I'm writing and where I'm sitting, and it's just clumsy. Follows a logistic. Hope I'm not spelling anything incorrectly. Because see, when I put my hand over there, I can't see, so it's just weird. With mean 0, standard deviation equal to 1. Now, fun stuff. Let's return to this pi over 3 business. So we can say that the probability that y sub I is equal to 1 equals pi sub I, which is equal to the probability pi over the square root of 3 times E sub I C over standard deviation of C is less than or equal to pi over square root of 3. Guys, all I'm doing is just multiplying what I had on the previous page by pi over the square root of 3. If I can see. All right, so notice that by doing this, multiplying by pi over 3, doesn't change the probability whatsoever. So guys, what this leads us to is to say that the probability of E sub L must be less than beta 0 plus beta 1 x sub I, which is equal to the cumulative function of beta 0 plus beta 1 x sub I, which is equal to, drum roll please, x sub I, where in this case beta 0 would be equal to pi over the square root of 3. You guys don't forget the significance of that. And beta 1 is going to be equal to, of course, the pi over the square root of 3 times beta 1 star. And these are the logistic regression. Make sure I'm spelling everything here. Parameters. All right, so where does this lead us? Probably a good place to sit back and summarize. What we can say now is that the expected value of our y sub I is equal to pi sub I, which can be, I think I've been used that, f sub L, the cumulative density function of beta 0 plus beta 1 x sub I, which, guys, again is E beta 0 beta 1 x over 1 plus E beta 0 plus beta 1. Let me see, I wrote that correctly because I can't see. Okay, so guys, a lot of emphasis on this right here. It kind of corresponds, if you will, back from the simple linear regression model where we had the expected value of the y sub i's could be found by beta 0 plus beta 1 x sub I. The counterpart to this is this expression in logistic regression. So, and by the way, an equivalent form, I'll just throw this out there because I had an issue with this come up in a undergraduate senior research project. So just sure there's no misunderstanding. An equivalent form of this is 1 plus, let's see, e to the negative beta 0 minus beta 1 xi to the negative 1 power. Now that could very possibly, well, could pop up as a test question, but who knows. So the drum roll please, we can say that the inverse of pi sub I, let's see what I'm writing here, is equal to beta 0 plus beta 1 x sub I, which we can call pi sub I prime. So this beast right here is called the logit transformation of the probability of pi sub I, and it's given by the natural log of pi sub I 1 minus pi sub I. Now, and should go without saying, but let's just say it anyway, that this is the odds. So taking the natural log of the odds is going to play, a critical role in getting our beta estimates into a form where they're more easily interpreted. Actually, we'll take the beta, raise it to the e power, but it's all connected, and it meets out there someplace. All right, guys, that's all I got.